In this video, we will be reviewing the objectives of Core M36. State the division algorithm for a polynomial ring over a field and demonstrate the truth of this theorem for given polynomials. We won't go into detail on the proof of this theorem. However, we will review an example demonstrating this theorem. The division algorithm. Let f be a field and let f of x and g of x be polynomials in f bracket x with g of x not equal to 0. Then there exist unique polynomials q of x and r of x in f bracket x such that f of x is equal to g of x times q of x plus r of x. And r of x is equal to 0, or the degree of r of x is less than the degree of g of x. So it's important to define what is what. We have that f of x is our dividend, g of x is our divisor, q of x is our quotient, and r of x is our remainder. Recall previously our division algorithm. B is equal to AQ plus R. This is the division algorithm that we were working with primarily with the integers. Compare how it looks to the division algorithm for polynomials that we are currently working with. We will be applying the same techniques that we did with the division algorithm for integers, similarly to the division algorithm with polynomials. Before we dive into an example, let's consider some helpful hints to use during the process of polynomial long division. Some helpful hints are to add 0 terms to keep terms lined up. You'll see an example of this in a little bit. Always check the powers before multiplying. Check the signs when dealing with negative terms, and check the power of the remainder. Is the power less than the power of the divisor? These are all things to keep in mind when going forward with polynomial long division. Example. F of x is equal to 2x to the fourth plus 4x squared minus 1. That is our dividend. G of x equals x plus 1 is our divisor. We are going to solve for our quotient, q of x, and our remainder, r of x. Here we have our example. X plus 1 is dividing 2x to the fourth plus 0x to the third plus 4x squared plus 0x minus 1. Here you can see we added in the 0 terms because in our original function we did not have a x cubed term or an x term. This will help us keep our terms lined up. To do polynomial long division, what we need to do is take the power of our divisor and match it up to the power of our first term. So we will need to multiply x by x to the third to get the power of 4. But we also need to consider the coefficient 2. So our first term is going to be 2x to the third. We are then going to multiply this by both parts of our divisor. So we will get 2x to the fourth plus a 2x to the third. Now with any division, we're going to subtract our terms. Our x to the fourths will go away, and we will be left with a negative 2x to the third. Now again, we need to consider what power we are trying to reach and the coefficient and how we will multiply something by our x term to get this. We will multiply by a negative 2x squared. Negative 2x squared times an x will give us a negative 2x to the third, and negative 2x squared times 1 will give us minus 2x squared. What we will also need to do is bring down our x squared term. Here we will see that our x cubed terms will cancel out, and our double negative will make this plus a positive. So now we will have 6x squared. Again, we will bring down our x term. However, this one will only be our 0x. So now we will multiply our x term over here by a 6x. 6x times x will give us the 6x squared we need, plus an additional 6x. With subtraction, our x squared terms now cancel, and we are left with a negative 6x, bringing down our negative 1. The last thing that we will multiply by is a negative 6. Negative 6 times x gives us negative 6x. Negative 6 times positive 1 gives us negative 6. Again, with our subtraction, plus positive, positive, reduce, and we are left with 5. Thus, we can say that our quotient, q, of x is equal to the polynomial 2x to the third minus 2x squared plus 6x minus 6. And our r of x is going to be 5. We can write that as 5 or as 5 divided by x plus 1.